very good for Zoom. So apologies for that. Want to welcome Professor Chungsik Yoo, who is going to give us a presentation on the practical use of geosynthetics in tunneling from a tunneler's perspective. Just want to give you a bit of background of what IGS is the International Geosynthetic Society, and we've got membership and chapters all over the world. As you can see on this side, we've got 45 chapters globally, and we are representing 50 countries. Currently around about 4,000 members across the world, including corporate, individual, and student members. There are a number of benefits to joining IGS, and the biggest benefit probably that I would think is the one that gives you access to the journals. I found that really useful in the past, and it is a huge plus to be able to get access to the two journals that is supported by the IGS, as well as the other benefits listed on the slide. We also have a job shadowing program. There's recently been emails sent out to provide information on the job shadowing program. And if you know of anybody, or if you're interested yourself, you can apply at the address provided down here at the bottom. It is of huge benefit to, I would think it is of huge benefit for people to see what is actually involved in designing with geosynthetics, in doing an engineering job, and figure out whether or not this is something that they would want to pursue themselves. We also have a summer internship, which is a 10 to 12 week placement in the industry, where you can gain experience over a longer period, and you actually get to do a project and learn more about the use of geosynthetics in the type of design work that we do. And now we have Professor Yoo. He's a professor of civil and architectural engineering and landscape architecture at SKKU in Korea. He currently serves as the president of the Federation of International Geoengineering Societies and is the immediate past president of the IGS. He's also been an executive council member of the International Tunneling and Underground Space Association, which I think is particularly cool, Professor Chungsik. Professor Yoo has earned his MSc and Ph.D. in civil engineering from Pennsylvania State University. And after a brief stint at Mueser Rutledge Consulting Engineers, he joined SKKU. He has held leadership roles, including the chair professor and vice dean of engineering. He has co-authored over 500 technical papers in geotechnical engineering and tunneling, and received the 2010 IGS Award. He's a member of the Korean National Academy of Engineering. He has also earned multiple national awards. Currently, he's editor-in-chief of Geotextiles and Geomembranes, which is one of the journals that you can get access to if you are a member, and serves on editorial boards of several leading journals in this field. Welcome, Professor Chungsik. And now I need to figure out how to change it to you.
Okay. So if you want to share, I will share my screen. Okay.
Yeah.
All right. Okay. I hope you can see my screen today.
Yes.
Thank you very much for your kind introduction. Thank you for reading all the long bio. Good afternoon, actually. Here in Korea, it's 11:10 p.m., 15 p.m. I guess in Australia, Sydney time is about 12:15, right? So lunchtime. So thank you, the Australian chapter of IGS, for inviting me to deliver this lecture. And today I will be discussing practical use of geosynthetics in tunneling And this topic has not been widely explored, but is gaining significant attention as the use of geosynthetics in tunnel construction continues to expand. So I will talk about first the introduction, tunneling 101 briefly. So first, let's go with the tunneling 101. Well, as you all know, probably I guess you all already know the construction method of tunneling. We have three different type of tunneling methods: cut and cover tunneling, drill and blast tunneling, and lastly, mechanized tunneling using TBM, tunnel boring machine. Here, the cut and cover tunneling and drill and blasting tunneling requires geosynthetics for the purpose of waterproofing. Well, cut and cover tunneling is typically used, as you know, for shallow tunnels and involves excavating a trench and constructing the tunnel structure within it, and then backfilling over the completed tunnel structure. Here, the waterproofing is done with geosynthetics, which are typically placed around the exterior of the tunnel lining before backfilling. And this method is widely used in urban environments for metro stations, underpasses, and also utility tunnels where surface disruption is manageable. Well, drill and blast tunneling. This is known as also a sequential excavation method of tunneling. And as you can see in the short video, excavation is carried out by drilling or blasting, depending on the ground condition. And after the removing debris, as you can see, we have to remove the debris. And then primary ground support is installed to stabilize the opening using shotcrete and or rockboards. They are steel ribs. And then you apply shotcrete. We call it sprayed concrete. And sometimes you install rock bolts as well. And this is the one cycle. So you repeat this and over again until full excavation is completed. So here the geosynthetics play an important role as waterproofing and drainage layers behind the lining, tunnel lining. Okay. So this is a recap. You excavate and install shotcrete and or rock boards. And here the geomembrane with or without drainage layer encapsulate the shotcrete area before the concrete lining placement. And then you install the concrete lining. And then internal works are done. Okay, so this is a step-by-step procedure for conventional tunneling. Okay. Lastly, mechanized tunneling. This is used in conjunction with tunnel boring machine or TBM. And this method is commonly used in urban tunneling projects, especially where minimizing surface disruption is critical. The surface disruption means settlement, for example. First, you launch a shaft and it's constructed where TBM will begin its drive. And then TBM is then assembled in sections at the bottom of the shaft. And the machine is begins its forward drive. Okay. So in this urban tunneling method, no geosynthetics are used for waterproofing. Instead, the gaskets between the lining segments are used. Okay. So let's take a closer look at the details of concept of waterproofing in tunnel systems. Okay. So I'm going to focus on conventional tunnels. I'm not going to talk about gaskets in TBM tunnels because they are not relevant for geosynthetics. So I'm going to focus on conventional tunnels. Okay. Okay, as you can see, and also you can imagine, constructing tunnels below the groundwater table creates a significant drainage system. Therefore, it is essential to clearly define how groundwater inflow will be managed, okay, whether through undrained waterproofing or drained waterproofing. Okay. In undrained waterproofing, a complete sealing system is applied and prevents the drawdown of groundwater table. So as you can see, no water inflow into the tunnel excavated area. On the other hand, drain waterproofing allows controlled groundwater inflow into a drainage layer. So this often results in drawdown of groundwater table over time. So this is the inflow variation with time. So a tunnel can be either sealed or drained, depending on how groundwater ingress is managed. Okay. In a sealed system, as you can see, sometimes you call the undrained tunnel. The waterproofing membrane is completely blocks water from entering the tunnel. In contrast, a drain tunnel incorporates a drainage layer to discharge groundwater in a controlled manner. Okay. Then which one we choose? The choice between the two systems is not just technical, but also contextual. That means it depends on local design codes and project specific constraints and environmental considerations. For example, in highly populated area or zones with sensitive ecosystems, undrained systems may be mandatory despite higher construction costs because we want to prevent the groundwater table lowering. But regardless of type, geosynthetics play a central role, critical role in waterproofing and drainage. Okay? So we will now look deeper into how these systems are designed and implemented. Okay, let's talk about the drained waterproofing system. So before placing the final concrete lining, now you can see the shotcrete area, drainage layer, the membrane, and so on. So this is concrete lining. After installation of membrane, we install concrete lining that can be 30 centimeters or 50 centimeters, depending on the ground condition. Okay. Now, the groundwater seepage through the shotcrete layer is intercepted by the drainage layer and directed to perforated sidewall drainage pipes. Okay, so you can see that this is ground, and you have primary lining, which is shotcrete, and then the water through the primary lining is intercepted by the drainage layer. Okay. So the critical advantage of this approach is that no hydrostatic pressure, which is water pressure, is exerted on the final concrete lining. So we can discard the water pressure for design. That means this significantly reduces the structural demand on the lining, meaning it can be designed to be thinner and more lightly reinforced. On the other hand, undrained waterproofing system is rather simple because a geomembrane is installed to fully encapsulate the tunnel envelope. So unlike drain systems, there is no provision for collecting or discharging groundwater, meaning water pressure is allowed to build up around the tunnel concrete lining. So this results in full hydrostatic pressure acting directly on the final concrete lining. And this approach is often adopted in urban or environmentally sensitive areas where preventing groundwater drawdown is critical. So you see the water pressure acting on the concrete lining. Okay. So this table summarizes the differences between the two. As you can see, drained waterproofing offers the advantage of allowing thinner and more lightly reinforced concrete liners, but it comes at the expense of maintenance costs. You have to do the maintenance a lot. Okay, we will talk about later about the maintenance. The undrained waterproofing, on the other hand, has advantages of low environmental impact associated with groundwater, but at the expense of thicker tunnel lining, which leads to higher construction cost. So again, the choice between the two methods must consider not only technical and economic factors, but also environmental constraints and project-specific conditions. Okay. So this slide illustrates the typical configuration of a drained waterproofing system. In this method, geosynthetics, either fleece or composite materials, are used to form the drainage layer, as you can see. Here, you see the geosynthetics drainage system. This is geocomposite. Okay? And then we install the geomembrane. Okay? So this is dry pack to collect the water. And then perforated pipes will act as a drainage pipe. Now, a range of specially manufactured geosynthetic products are available on the market, especially in Korea. And these products combine multiple functions: filtration, so you see this geotextile, and drainage by geotextile, sometimes geocomposite, and geomembrane for waterproofing. Okay. So these all-in-one type products simplify illustration and illustrates how the water can be handled for a tunnel structure. Now, as I mentioned, geosynthetics are heavily used in tunnel waterproofing, but they must satisfy technical requirements. So let's start with geotextile. For geotextile, starting with chemical resistance, geotextile need to withstand alkaline environments because the surrounding ground and construction materials like concrete and grout can release calcium hydroxide, as you know. That creates a chemically aggressive condition. In terms of mechanical performance, geotextiles should have sufficient mass per unit area, tensile strength, and puncture resistance. So you can refer these indicative values, okay? Although these numbers may vary depending on local design standards and project specifications. In addition to these properties, the hydraulic transmissivity is another important performance indicator as a tunnel drainage layer. So as you can see, we have to understand the role of geotextile or drainage layer here. Okay. So once it is installed, it can be either clogged, right, as you can see here, and the thickness can be decreased due to the ground pressure or lining installation pressure over time. See? So thickness decreases. Okay. So you can see if we don't have any ground pressure after excavation, we can have some thickness, as you can see. But with time, ground pressure will develop and thickness may decrease, as you can see. So the thinner the geotextile, the smaller the discharge capacity. So we have to consider this the physical phenomenon when we choose geotextile, for example. Okay? So we typically recommend a minimum transmissivity of 4 times 10 to the minus 6 meters squared per second at the pressure of 150 kPa. Okay, but this value can vary region to region depending on the local code. Okay, now this table wraps up and summarizes the technical specifications required for geotextiles in tunneling community across various international guidelines in Germany, Switzerland, in Asia, and so on. As you can see, although specific values may differ by country or agencies, they consistently require geotextiles with sufficient mass per unit area, tensile and puncture strength, and in-plane permeability. Okay, so most standards specify polypropylene materials, and the transmissivity values typically ranging from 10 to the minus 6 to 10 to the minus 3 meters squared per second, depending on the application. Okay. So let's talk about geomembrane. Okay. As I mentioned before, geomembranes is basically used as a barrier to keep water out of the tunnel, just like any other application, just like in landfill. Well, as highlighted by our past president, Daniele Kazufi, a geomembrane is just right product for this purpose for tunnels, as it forms a continuous and almost completely waterproof enclosure due to its very low permeability. You know, also it can stretch a lot, over 200%. So it can cover cracks in the concrete lining without tearing, right? And another big plus is good weldability, as you can see, okay? Now, among the different types, PVC membranes are the most commonly used, not necessarily because they are better, but mainly because they've around the longest, okay? These are the technical requirements for geomembranes defined by different countries or projects on their application. As you can see, minimum thickness of 2 millimeters is recommended, but it can increase to 3 millimeters when pressure is considered. Pressure can be ground pressure after excavation, lining installation pressure after excavation, and so on. Okay, so please refer to this table for typical mechanical properties. Okay. Well, let's talk about Korean tunneling just a little bit to give a sense of how serious we are in tunneling. Well, Korea has made significant investment in infrastructure development since the 1960s, following its recovery from the Korean War, 1950s. Okay, so one of the most transformative projects has been the development and construction of the high-speed railway system, as you can see in this slide. The first phase began in 1996, focusing on the construction of the Gyeongbu line that connects Seoul to Busan. That is a 410-kilometer route connecting, as I mentioned, Seoul to Busan. Busan is the second largest city. Okay. And this line was completed and put into service in 2004. So this is Gyeongbu line. Okay. And building on that success, another line, which is Honam line, was constructed. Okay. Connecting Seoul to Mokpo. Mokpo is probably maybe fourth largest city or fifth, the southern part of Korea. And this line was completed and put into service in 2017, more recently. Okay. So these two lines form a 660-kilometer high-speed railway network in Korea. We have another plan to build more lines, but this network has revolutionized the travel across the country. Well, the other day, I mean, before this system, this railway, 2 days were required to travel to Busan, but now it's 1 day travel. You take the train in the morning, have a lunch in Busan, and come back in the afternoon. Okay, so we love this system. Now, during the construction of the second line, which is Honam line from Seoul to Mokpo, we built a Yulhyun tunnel. Yulhyun tunnel from here, location station called Susa to Jije. The length, 50 kilometers, 50 kilometers. So at the time of construction, completion, it ranked as the third longest railway tunnel in the world. Okay. The diameter is about 13 meters. The length, 50 kilometers. Okay. Let's do some math here. Okay. Again, tunnel has about 10 to 13 meter diameter, runs for 50 kilometers. So if we assume we are covering just 10% of the total surface area with geosynthetics, that is already over 345,000 square meters. If we break down in terms of materials, we typically use PVC or HDP geomembranes as a waterproofing layer and geocomposite. Yeah, you have the number here. Estimate total, 12 million US dollars. Okay. So it's a lot of money. As the tunnel is longer and longer, the cost for the geosynthetics will increase, as you can see here. Okay. Okay. So now we have talked about the fundamentals of waterproofing. Now I focus on my talk on the conventional tunnels for drained tunnel waterproofing system. Okay. Unfortunately, a drainage system for drain tunnel deteriorate over time. Okay. So we build a tunnel to last 50 years, 100 years, sometimes more than 200 years. Unfortunately, the drainage system can deteriorate over time for many, many reasons. So I will talk about this issue under the title, Hydraulic Deterioration of Tunnel Drainage. Hydraulic deterioration can occur by two reasons. As you can read here, one by clogging and by reduction in thickness. Okay, so let's start with clogging. Okay. The drainage layer gets clogged by soil particles and or calcium carbonate. Okay, calcium carbonate in water. Because we are talking about water flow, right? From the groundwater, from the ground through the shotcrete layer and through the drainage layer. So we have groundwater flow, right? So that groundwater flow can carry soil particles and calcium carbonate, right? So if drainage system clogged, as you can see on your left, by soil particles or by calcium carbonate, then we have problem known as clogging. Okay, when clogged, then unwanted water pressure behind the lining will develop. So to better understand the effect of clogging on the hydraulic performance of a drainage layer, a series of lab tests were conducted by researchers. What you see here are the setup for vertical permeability and discharge capacity tests. In this series of tests, a specially prepared calcium carbonate solution was used to compare the pure water and calcium carbonate solution. What are the effects? To see what are their effects, okay? So here are the results. You can clearly see from these two graphs, one using pure water and the other with calcium carbonate, okay? You can clearly see that for a given confining pressure, when the calcium carbonate solution flows, you can clog geotextiles and you have problem. Okay? So this really highlights why it is critical to account for potential clogging when designing tunnel drainage system. Okay, another major reason for drainage system deterioration is additional pressure imposed after the installation of drainage layer. As I mentioned, after excavation, ground can deform, right, against concrete lining, right? So the drainage layer subject to normal pressure acting against it, okay? And also, once drainage layer is installed, then concrete lining will be constructed. And during the construction, it can impose additional pressure, installation pressure to the drainage layer. So all these pressures make the geotextile drainage layer thinner. As a result, the flow path narrows and drainage capacity drops. And once again, we end up with unwanted water pressure acting on the lining, okay? So to wrap up, so this is intended design scenario for a drained tunnel. Supposed to be no water pressure acting on it, right? This is intended, okay? When drainage layer deteriorates, as you can see, now it becomes partially drained or undrained tunnel. Unwanted pressure, water pressure will develop behind the lining that can create structural problem to the lining. So you have to remember what is intended design and what is the consequence of lining a drainage layer deterioration. Then what happens? So let's talk about what actually happens when the drainage system deteriorates. Okay, you see the lining cracks, right? And also this is numerical simulation for no clogging and with clogging for particular clogging scenario. You can see that lining bending moment increases 3 times more than no clogging when we have clogging here. Okay, so this is 0.7 meganewton meters. But when the lining is clogged, the drainage system is clogged, lining bending moment increases 2.1 meganewton meters. So what is the consequence? Lining failure, as you can see here. Okay? So this clearly shows that the hydraulic deterioration by clogging is a serious issue, as it can compromise the structural safety. Another example from China. This case history reported by Zhang et al. In 2020. So this is a typical horseshoe-shaped tunnel, about 400 meters long. And this is designed as a drain tunnel system, but during operation, something happens against design intentions. The tunnel is experienced deterioration due to a drainage failure, and these are the consequences. Okay. So due to drainage system deterioration, cracks began to form in several locations. You can see and hunch levels, the spring line, and inbutt level. You can see the water coming out from the cracks. The cracks were developed because of the unwanted lining, the water pressure that created cracks, and water seeped through the cracks, right? So this illustrates how important it is to consider the hydraulic deterioration of a drainage system. So this is probably the most common problem in terms of operation maintenance for conventional tunnels. Numerical simulation to see better identify what are the effects of hydraulic deterioration. So in this analysis, we did a sophisticated coupled analysis, water and mechanical and hydraulic interaction problems. 7-meter diameter tunnel was considered, and a range of hydraulic deterioration cases were considered, okay, to see what are the effects of hydraulic deterioration scenarios on the structural performance of concrete lining. So these are the ground type 1, type 2, type 3, and lining, as you can see. So I'm not going to go detail about the modeling. So let's take a look at what can happen. So this is intended, undrained. This is intended, okay? Drain tunnel. However, when hydraulic deterioration happens, the water table goes back, all right? Imposing additional water pressure on the concrete line. So depending on the degree of deterioration, no deterioration, you can see that the zero water pressure around the lining, and moderate deterioration, some water pressure developed, and full deterioration, as you can see, full hydraulic pressure exerted on the concrete lining. And this shows you the actual thrust developed in the concrete lining and bending moment development depending on the degree of deterioration. You can clearly see that when deterioration occurs, the bending moment and the thrust of the lining increases as well. Okay, let's talk about the practical. So what do we do? So let's talk about what should we do, okay? So I'd like to shift gears and move into the design of tunnel drainage system from an engineering practical perspective, engineering practice perspective, okay? There is no theory, just practical application, all right? So when using geosynthetics like geotextiles or geocomposite in the drainage system, they serve two important roles. They act as a drainage and also at the same and as a filter, right? Geotextile works as a filter. So in order for us to avoid hydraulic deterioration by clogging, we have to talk about geosynthetic filter design principles. Okay. So as you may know, there are three fundamental criteria that should guide the design of geotextile filters. They are retention criteria, permeability criteria, and also anti-clogging criteria. Okay. So of these criteria, the anti-clogging criteria is most relevant for tunneling problems. Okay. Now, if you take a look at my paper, published in, I believe this is 2016, you can see that. The details of the clogging criteria and design of tunnel line and system, the drainage system is well described. So please refer to my paper published in Geosynthetics International. Okay. Well, as I mentioned, among the 3 filter design criteria, the anti-clogging criteria is the most relevant, which consider the relationship between the fine particles in the soil and their ability to block or blind the openings in the geotextile, as you can see in this illustration. So a number of empirical criteria are available, as you can see, which relate the particle size characteristics of soil and the pore size of geotextile. Now, for critical or severe applications, rather than using these empirical formulas, it is recommended to perform a filtration performance test known as gradient ratio test. Okay. So this slide illustrates the setup for a gradient ratio test. As you can see, we simply place soil over the geotextile layer, which is drainage layer, and apply a vertical hydraulic gradient. The key parameter here is a gradient ratio, which is GR, defined as a ratio of the hydraulic gradient at the soil geotextile interface to that within the soil itself. So I sub SG is hydraulic gradient at the soil geotextile interface, and IS, that is hydraulic gradient within the soil itself. Okay. So usually GR value less than 3 is generally considered acceptable, but 1 is preferred. Okay. So by performing the filtration performance test, which is gradient ratio test, we can evaluate the potential for clogging. I think that is very important. So in Korean tunneling, the sites, we applied the anti-clogging criteria together with gradient the test as well. Okay. So this table on the left summarizes the physical properties of soil collected two sites, and also the properties of candidate geotextile 2, geotextile A, and geotextile B. Okay. So all these parameters obtained from the soil taken at the site. So this table summarizes the result of clogging potential check. As you can see, geotextile A and B fail in most checks. Why? Because they are very conservative. Okay. Those empirical criteria are very, very, very conservative. However, when applying gradient ratio test, both geotextile A and B showed GR values less than 3, okay, which is below the critical threshold of 3. That means they are acceptable. Okay, they will not clog under the given condition. Okay. So my recommendation is, even though the empirical formulas are conservative, let's check the clogging potential with the empirical formula together with the physical performance test, which is gradient ratio test. Okay. And doing this is better than not doing it. Okay. So finally, this is the proposed practical approach. For tunneling problem first, either you or other design engineers should conduct the seepage analysis to estimate the water inflow rate for the tunnel under consideration. Okay. And then use this result to assess whether the candidate geotextile or geocomposite has sufficient discharge capacity. And then use at least 4 millimeter thick geotextile when it functions as the drainage layer. Okay. Now we have to, in this case, we have to account for the thickness reduction of the candidate geotextile on the confining pressure that I already talked about from the ground and from the lining installation to ensure that we have enough long-term discharge capacity. Okay. And then perform filtration clogging test, gradient ratio test, using the soil taken from the site. Okay. Now I'm talking about the practical approach that we have to do during the design. Okay. So based on the result of gradient ratio test, compatibility with drainage function, drainage layer with the soil can be checked. And also we can check the long-term residual flow capacity by checking the clogging potential due to the soil particles and so on. Okay, so this is step-by-step procedure that can be done. So doing this much better than without doing nothing. Okay. On the current design procedure, you don't have to do this. Under the current design standard, you don't have to do this. You don't have to perform the clogging test, gradient ratio test, but in order for us to correctly use geosynthetics, if we follow this procedure, we can eliminate or reduce the potential for clogging of drainage layer, which is geotextile or geocomposite. Okay. So I think this clearly defines how we approach these things. Okay. So that we can prevent clogging problems during operation. So in concluding remarks, and in this presentation, fundamental aspect of drained and undrained waterproofing of drill and blast tunnels are presented. And also critical roles of geosynthetics, geotextile, and geomembranes in particular have discussed. And concept and the governing mechanism of hydraulic deterioration has been discussed here. And practical approach is discussed in this presentation. Okay, I believe the practical approach that I proposed, can reduce the risk of clogging potential when we use geosynthetic as a drainage layer in a drain tunnel of a conventional tunneling. Okay, an important message that I want to deliver here is that geosynthetics are not commodity, as we all know, right? They are engineering products which need proper design. I think my lecture focused on this today, and hope you can also follow. With that, thank you very much.
Thank you, Professor Yoo. I have 3 questions on the Q&A.
Okay.
I'll read them. Why is PVC preferred over HDP or LLDPE as geomembrane for tunneling projects? And you mentioned cost being one of it. Or
Well,
not the cost, the fact that it's been around the longest. Is there another reason?
well, that is the most probably I would say the reason for PVC. PVC is most widely is because of it has been around for longer time. That is the reason. Okay, that doesn't mean HDP or other type of geomembrane is better. I'm not saying that. That is just based on the statistics offered by International Tunneling Association. Pure reason. It has been around for a longer time.
It's proven itself. It's got a track record, and people are not willing to change necessarily because they have something that works.
But we can definitely try other type of geomembrane. Yeah.
Thank you. Then the next question is, with the high risk of hydraulic deterioration, would it make more sense to design tunnels as undrained tunnels?
Sorry, can you repeat one more time?
With the high risk of hydraulic deterioration, will it make more sense to design tunnels as undrained tunnels rather than drained tunnels?
Well, in terms of the cost, the undrained tunnel is more expensive than drained tunnel. Okay. So I don't think designer would, the local authority wants to have a drain tunnel, undrained tunnel because of the clogging potential. What we can do is we can reduce the clogging potential by doing proper design of drainage system. I would put that way. Yeah.
So the cost of a drained tunnel versus an undrained tunnel, what's the difference in cost? Like 10 times more, 2 times more?
Well, it depends on the ground condition, but you can say, I said for the undrained tunnel system, we need thicker lining, right?
Yeah.
Thicker lining means in order to have the space clearance for the tunnel, we need to excavate more.
Yes.
More excavation, more money, and we need more cost for concrete, so it is much more expensive. And technically, it brings in a more difficult situation. So, so in that sense, unless local code specifies you have to use undrained tunnel system, mostly we adopt the drain tunnel system. But if tunneling is done on the very historical area and we don't want to disrupt the ecosystem, then we have to go and we are required to go undrained tunnel. But mostly, at least in Korea, we use the drain tunnel system.
So all other things being equal and not taking into account the environment, etc., which one is the riskier one, the drain tunnel or the undrained tunnel, do you think?
The riskier one, definitely in terms of maintenance, the drain tunnel is most riskier because, always the drain tunnel system means there will be water flow. That means water flow carries soil particles and, calcium carbonate that clogs over time anyway, right?
Yeah.
We can reduce the potential for clogging by doing the proper design of geosynthetics.
So brings me to my question for myself is, in terms of, you obviously add a factor of safety to the drainage system in terms of how thick or wide or the flow capacity. What is the typical factor of safety that you would add to a system like that?
Well, factor of safety, we can go with 2, or if the ground condition, for example, and if a lot of fine-grained soils are present, then we can go factor of safety 3 too, right? Depending on the designer. Right?
Okay. I'm just wondering because for drainage systems, for dams, for instance, or for tailings facilities, we very often go for a factor of 10. We're like much higher. So yeah, it's just interesting to see the difference in choice.
I think we have to understand that the importance of geosynthetics in tunneling has not been recognized until recently,
Yeah.
right? So
Yeah.
as we establish fundamental mechanisms and the result of more research and get more data from the field, and maybe we have to increase the factor of safety like dam systems. But I think the reason we have some gap between what we know and in the field is because the importance has not been recognized until now.
Okay.
Yeah.
Okay. Interesting. I've got a question from Jonathan. He wants to know whether you've got any comment on the choice between polypropylene and PET non-woven, non-needle punch geotextiles in critical applications given neutral pH range of 5 to 9.
Well, that is not my specialty area. I leave it my answer to the expertise. I mean, it's not appropriate for me to mention it. That's very dangerous too. So anyway, you understand why
Jonathan is asking everybody that question at the moment, so you know, you're not the only one.
but the PowerPoint presentation that I have today, I presented two tables for the geotextile and geomembrane. I think they are quite commonly agreed properties, and so you can refer to that too. Okay.
So, is there any PET geotextiles that's manufactured in Korea? Do you know of any?
I don't think we do.
Okay.
I think in Korea we have a manufacturer that makes that geotextile. Yeah, we have many manufacturers, but nowadays, you know, not many manufacturers are around.
Okay. And then we've got a question from Herman. Is fire resistance essential and required for geomaterial in tunnels?
In Korea, the standard, because it is installed behind the concrete lining. Okay. So we have talked about it, but that has not been implemented in the code. Okay, fire resistance and so on. But I think that is very important because now, we are having a lot of fires in tunnels because we have many tunnels. The Korean Peninsula, 70% of the land is mountains. Okay, so we have many tunnels, and also nowadays we have a lot of the fires in the tunnel because of the accident. I think that important issue has to be addressed in the future. We are talking about it, but currently it's not being addressed.
Okay. It's like the drainage factor aspect as well, because it's new, it's still developing.
Exactly, yeah.
Yeah. Cool. Well, thank you very much. This has been incredibly interesting, and I loved hearing about all of this. So thank you for your time, and thank you everybody for attending. I appreciate your time.
Thank you very much. I'm really happy to meet you guys, and in the near future, I hope to see you in person soon.
Excellent. Perfect. Thank you.
Okay, bye-bye.
Bye.